All right, we're back. We're on page 10 of note 17 of Calc C. We're doing polar areas. We're doing weird problems mostly where like you wouldn't ordinarily describe them with polar coordinates, but I think that's by far the best way to learn to do polar areas. So it's a weird kind of dichotomy. So this region is actually terrible to describe in polar because it lacks almost every property that you would want a polar region to have. It's like all straight lines. It's also like not a consistent outer curve as you go through. Like it's just a disaster. But let's see if we can do it. So we have y equals 2x plus 3, and we have x equals 5, which means this ordered pair right here is 5, 13. Which means that let's think about what we're doing. So we're going to start facing here, and we're going to rotate. And as we rotate, we want to keep in mind, like, where is our laser beam hitting? So for a while, our laser beam is hitting this vertical line. But then when we get to the point 513, we stop hitting that. And we start hitting this line, the slanted line. So actually, we're going to have to do two separate integrals to get this. And that's kind of unfortunate. So what is this line? So we're going to go from the origin through here. Okay, let me try to move it. Okay, so this line right here is going to be the inverse tangent of y over x, 13/5. So that's theta. Okay, so two separate regions. We're going to start at 0. Come on. Just do the line. Just do it. It's because I don't like stop well enough. It's discriminating against my jittery hands. Okay. We're going to start at theta equals 0. And we're going to rotate. Where are you? Okay. We're going to rotate through the region from 0 until we get to inverse tangent of 13/5. Oh, I see what happened. You turned this into autocorrect is killing me. From 0 to inverse tangent of 13/5, the curve that our laser beam is hitting. I'm actually using a laser pointer type tool, so like it actually is kind of a laser beam. Is going to be x equals 5, but x equals 5 means that r cosine equals 5. So this is actually r equals 5 secant theta. Okay, so that's region 1, and maybe I'll label that region 1. That's not really a good one, region 1. Okay, so let's describe it. Region 1, we have r is going to be 5 secant theta, and we have that theta is between 0 and the inverse tangent of 13/5, which like where, I don't know. I mean, we don't really need, I don't think we need to use a calculator on that one. Maybe. All right, next up. So we're going to start rotating here and just kind of go this way until we hit. So now here's the weird thing, right? You're shooting out lasers and you're hitting and you're rotating and you're hitting. You keep going until you get to pi over 2. Like it feels weird from a like rectangular standpoint, but you have to keep rotating until you hit theta equals pi over 2. And the outer curve, the thing that you're hitting all the way through that region, imagine doing it, right? It's like a weird line. You're going to keep hitting this all the way through until you're at pi over 2. Once you're a little past pi over 2, you're not in the region anymore. So we're going to go from 0, not 0, we're going to go from the inverse tangent of 13/5 until pi over 2. We need to write this curve in polar. This curve is not really meant to be written in polar, but that's not going to stop us, right? So this is, it's y equals 2x plus 3, right? I'm pretty sure. Yeah. Okay, so that means that r sine equals 2r cosine plus 3. So move over and factor r, I get sine theta minus 2 cosine theta equals 3. So actually I'm getting that r is 3 over sine theta minus 2 cosine of theta. Okay, so let's describe region 2. So region 2 goes from the inverse tangent thing until pi over 2, and it's that weird function. So R2. There's a way to integrate that, but like, it's not really, it's definitely beyond the scope of this video, and it's not really like fun. It's like a weird substitution that offhand I do not remember. It's got something to do with like cotans in there, maybe? Maybe? I don't know. I'd have to look it up again. It's like some crazy universal substitution that you can do. Like the strangest of substitutions. Maybe I'll look it up and then try to do the problem with that in a separate video though, not really relevant to the notes. All right, so if we want the full area, keep in mind, this is a trapezoid. It's a trapezoid that has a height of 5. So like, if we just geometry this thing, it's gonna be 1/2, a height of 5, and then the bases are 3 and 13. So 16, 8, so 40. I'm expecting to get 40 as my answer. We shall see. So it's going to be 1/2 the integral from 0 to inverse tangent of 13/5. If you think we're using a calculator, you're absolutely right. Secant theta squared. But you got to handwrite this part, otherwise nobody knows what you're doing on your calculator. Tan inverse. And also, like, we know that we can get the answer with geometry, so you obviously need, this is going to be a pain. Okay, to the calculator. So what am I going to define? Like maybe a lot of things. Let's see. Because like you want to make your life easier when you're doing these polar areas. So let's go new problem. We're in radian mode. That's good. I'm going to define R1 of t to be 5 secant of t. R2 of t, I'm going to define as 3 over sine of t minus 2 cosine of t. And then I'm going to define like k to be arctan of 13/5. Okay, and then I decided to do that. Good for it. All right, let's do it. 1/2 integral. So even though I can type it, it's actually kind of easier to use the template. So obviously I recommend that. We want to go from 0 to k of R1 of t squared dt plus 1/2 integral from k to pi over 2 of R2 of t squared dt. And I'm thinking I should get 40. Woo! 40. Nailed it. If you want to play around, it's like super, it's just interesting. Like integral of R2 of t squared. What? Right? R2 of t is this. If I square that, I get this. Look at that. So the integral of this thing squared is like kind of this thing almost. I don't know. It's got it. You should definitely be able to work that out. Like that looks simple enough. They look very related. You know, it feels like you're trying to reverse the quotient rule to me. Like that's how when I see that, I see a denominator squared, you know, and then I go and I integrate it and I get just the denominator. So I feel like, all right, there must have been a quotient rule thing going on. There's some kind of numerator, and you just kind of like work from there. So you can potentially work it out. I definitely recommend that you like try. So what's left in these notes? I'm gonna do it. I don't know how long that'll make a video, but at least I didn't try to integrate that thing by hand, which would have made the video 1,000 hours. All right, so let's see. The smaller region formed by intersecting the circle and the line. All right, this one, like you might actually use polar on. Like you might not, but you might. Like you could do triangle, right? Do like quarter of the circle minus the triangle, and that should give you the answer. That's not what we're here for. we're here to do polar. So first, what are our polar curves? Well, this is going to be r equals 10 cosine. How do I know that? It's tangent to the origin, centered on the positive x-axis, diameter of 10. R equals 10 cosine. I also know that this takes 0 to pi to graph. And I know that just by like the geometry of it, it gets to this point, the 0.55. Is that the 0.55? Yeah, I guess it has to be the 0.55. If you've been watching, I've been messing that up a lot. It gets to this point at theta equals pi over 4. Let me put that line in. So this is theta equals pi over 4. All right, now what do we want to do? Think about how polar is traced out. We start at 0, we shoot a laser beam, and then we're going to rotate this way and keep shooting laser beams. We're not hitting the region, not hitting the region, not hitting the region, not hitting the region, not. If we get to pi over 4, we start hitting the region. So what we want to do is rotate until pi over 4 with our laser turned off, get to pi over 4, turn the laser on, and start hitting the region. And then we just want to keep going until we get to this point. After this point, we won't hit the region anymore. So we need to stop when we get to pi over 2. It's really essential that you know how these things are traced out. If you don't know how the polar curves are traced out, you won't be able to work out the bounds of your integral. So like go back, make sure you are great, like literally like as good as you can be at graphing in polar. If you know that, you can work out these kinds of things. So I really just want to do pi over 4 to pi over 2 of this. Well, this thing squared. I mean, that's the outer region. So to describe the region in polar, I'm going to have r equals 10 cosine. And then for the region, I want to go pi over 4 to pi over 2. And that should give me what I'm looking for. So this will be 1/2 the integral from 0. Nope. I always want to do 0. I don't know. Pi over 4 to pi over 2 of 10 cosine. Maybe I'll do this one by hand. Although maybe I should remember how long this video already is. But I think I'm going to do it by hand. Because it's like such good practice. And also, if you don't want it to be a long video, you know, skip ahead. Or whatever, you know, speed it up, do whatever. Cosine squared is 1/2 1 plus cosine 2 theta, so this will become 25 because of the 1/2. And then I'll get 1. I know that that's wrong. I'm going to fix it. Get this, change you to the 2 that you're meant to be. Okay, so we get 25 theta plus 1/2 sine of 2 theta, pi over 4 to pi over 2. Now we got to sum in. So 25. This is one of those instances where like things don't all zero out. So pi over 2. The sine of pi is 0 though. Minus pi over, ew. I should have put this in parentheses. Minus the quantity, pi over 4. The sine of pi over 2 is 1. So plus 1/2. So this is 25 1/2 minus pi over 4. So 25 over 2 minus 25 pi over 4. How does that work out with what we thought we could do geometrically? So geometrically, I think that this is like 5 by 5. So this would be 5 by 5, but it's half of it. So that's 25 over 2. And then this is a quarter of a circle that has a radius of 5. So it should have been 25 pi over 4, which I think I didn't get, minus 25 over 2. Why didn't I get that? 25 pi. That's interesting. I have them flipped. The big thing minus the little thing. It definitely should be that. Why do I have them flipped? Oh, because I just wrote it wrong. Good job, me. This is supposed to be pi over 4 minus 1/2, which would have given me, it's a good thing I went back and did the geometry, right? Should have given me this, 25 pi over 4, which is like the quarter circle, minus 25 over 2, so like half a triangle. Half the triangle? No, it's the full triangle. It's half the square that we, it's half of the square that we cut in half to get the triangle. Okay, there you go. So this one's really polar. Like, I think you might actually do polar on this. Sometimes on math contests, I'll use polar on these types of things when they like describe a region. It's like just faster if you have a calculator. This one's crazy. Use a calculator on it, but you still get 40. You get the answer. So if you're getting these answers, I think you're on your way to knowing what you're doing. So I'll be back in the next video to do some more polar areas with you. So I'll see you there.